So I'll make the introduction in English, of course. So we have Mike Cushing with us today. Very happy about this. It's a special seminar, right? Brown dwarfs, unusual for many people. Mike Cushing is an expert in brown dwarf observations. He's been working on this since it's his PhD and master thesis. So which he did in Hawaii on the Oahu on the Manoa campus of University Hilo, master thesis and PhD there, where he developed the spectral analysis package. So he's an expert in data reduction and infrared observations. And he has an interesting life as a postdoc. I think quite a long life as a postdoc. 3 different postdocs over about 6 or 7 years in Arizona, UH in Hawaii, and JPA, right? So Stewart Observatory in Arizona. Yeah. So 6 years of postdoc. So hang in there, postdocs. I'm gonna get a job. And he got a job at the University of Toledo in Ohio in 2011. He's still there. And what's interesting about what he's been doing is that he's an expert on data reduction, but also brown dwarfs and spectral classification of brown dwarfs. One of the few people alive who has established a spectral classification. I mean, when you think about it, very few opportunities arise to do that. And he's done this for the LT and late M brown dwarfs in the near infrared, and then he did the same with Spitzer in the mid-infrared, okay? And guess what? James Webb is repeating this on the wide dwarfs, or doing something close to it on the wide dwarfs with MIRI data and near-spec data. And I believe that's what he's going to talk about today. So, so maybe there's an upcoming spectral classification in the mid-infrared with Webb, who knows? Cushing. So, thank you for and give him a warm applause for coming.
Thank you all for having me. Enjoying my visit so far. The spectral classification thing, I won't get into. If you want to ask me at the end, I can give my opinions on that. So today I'm going to tell you about our work with the Cycle 1 James Webb program to start probing the fundamental properties of the coolest brown dwarfs known. I want to lay out the team. It's a relatively small team. These are the people that I was on the proposal with. Sam Byler is a graduate student at the University of Toledo with me. Adam Schneider was a postdoc I worked with. He's at the United States Naval Observatory in Arizona. And then David Kirkpatrick, who is at IPAC and Caltech. Along the way, we've recruited some people. Another graduate student named Partial at the university. Mark Marley is a longtime collaborator of mine since I was a graduate student. He's now the director of LPL at the University of Arizona. And then Sagnick is a graduate student who we met recently and has been helping us with a lot of the modeling efforts for these data. I want to note that the work done that I'm going to present to you today is done almost entirely by these 2 graduate students, Sam and Marshall. I have to admit, this is the first time I have ever given a talk where the work I am presenting is not my own. And I don't know if that means I've arrived as a professor, right? Like I've hit the pinnacle of professorness, or this is just the first step in my obsolescence. I'll go with the former and hope for the best.
The answer is yes.
The answer is yes, yeah, right. Okay, so the roadmap for today is I want to give you the salient properties of brown dwarfs that you need to understand in order to understand the rest of the talk. And I want to motivate why we even decided to try to use Webb for these observations. I'm going to talk a lot. The biggest part of the talk is going to be on one particular object, WISE 035904, sort of a case study, all of the things that we're doing to these spectra. And then if I have time, just a very sort of short introduction to the population as a whole. We're still working on the data. As I said, this is really a progress report. There's a lot to be done. And so I'll show you a handful of slides, just giving you all the data at once. You can see the sort of beauty of all the data that we have. Okay, so part 1 is the properties and the motivation for the program. So a definition right? What is a brown dwarf? For those of you who don't know, it's an object that cannot achieve an equilibrium configuration where the radiative losses from the surface are balanced by energy generated in its core, which is a fancy way of saying they don't have a main sequence, right? So stars, we know, form, they hit the main sequence, and they fuse hydrogen into helium, and that's why they shine for billions of years, at least for the lowest ones. So brown dwarfs don't do that. They don't have fusion. As a result, like embers plucked from a fire, they cool off over time. They evolve, right? Whereas stars just sort of sit on the main sequence for billions of years. This is a sequence of models showing the effective temperature of objects of various masses. On the y-axis, you have temperature going from 0 Kelvin up to 4,000 Kelvin. The sun is another 2,000 Kelvins above that. And then on the x-axis, you have logarithmic age from 1 million years up to 1 billion and 10 billion. And every line is the evolution of the surface temperature of that mass. Up at the top, you have an object which is 2/10 the mass of the sun, or 200 Jupiter masses. And then you work your way all the way down to 1 Jupiter mass. So this is the evolution of the temperature of Jupiter over its lifetime. Stars, which are at the top, when they hit the main sequence, they reach this equilibrium configuration, and they just sit there at a fixed temperature, 0th order. And so that's what's happening. The 0.2 solar mass star comes down, it cools off, and then it just stays at that temperature for, you know, something like 1 trillion years, because these are really low mass stars. As you go to lower and lower masses, you eventually reach a point at about 75 times the mass of Jupiter, where that equilibrium configuration cannot be found, and you just keep cooling off. And so that's what's shown here. So an object of, say, 13 Jupiter masses will start out at 2,500 degrees Kelvin, sort of star temperature, but it will cool all the way down to several hundred degrees after 10 billion years. It's a massive change in temperature. And so it has a dramatic impact on the atmospheres of these objects. At these temperatures of a few thousand degrees, they have molecules and condensates in their atmospheres. This is very different than people who study stars, where you're worried about atoms in various ionization stages. This is a figure from a nice review back in 2014, which shows the mass fraction as a function of temperature. So this is the sun at about 6,000 degrees, and it goes down this way to cooler objects. And as you cool off, you see that eventually molecules and atoms switch. That is, molecules become the dominant mass in an atmosphere. And if you go cold enough, down below 2,000 degrees, you pick up condensates. These are literally grains of things that will condense out of the gas phase. You might form rock or liquid iron droplets or even water ice, right? So they literally condense out of the gas phase. What are some of the things that form in these atmospheres? So this shows you the log of the abundance of the species relative to hydrogen. So hydrogen is at the top at 0 versus the atomic number on the x-axis. And so the prominent atoms that you normally think about are sort of on the diagonal. Hydrogen is primarily a molecular hydrogen. Carbon, oxygen, and nitrogen are in water, CO, methane, diatomic nitrogen, ammonia, sort of the normal species that we sort of have in our atmosphere. Refractory things like magnesium, silicate, and aluminum go into these condensates, these dust particles. Sulfur goes into hydrogen sulfide, phosphorus, and phosphine, and just a menagerie of molecules. And this is just a limited picture. There's a lot more that can form. Once these condensates form, we believe they gravitationally settle and form clouds, very much like we see on the surface of Jupiter. So this is just a cartoon of that process to give you a sense of the complexity and the number of clouds that can form in these atmospheres. So stars are off to the right, where it's very hot. You don't have condensates, right? It's just atoms and molecules. And as you cool off to the left, the condensates form, they gravitationally settle, and they form a cloud layer. So when you first enter sort of brown dwarf regime around 2,000 degrees, you'll pick up perovskite and corundum, and then liquid metal iron and silicate like enstatite and forsterite. And then as you keep going cooler, more and more things condense out of the gas because you're getting colder and colder. And so those clouds are deep in the atmosphere, and you start picking up things like potassium chloride, right? And then you get all the way down to Jupiter, and you've just got cloud upon cloud upon cloud. And so you have the ammonia clouds on top, the ammonia hydrosulfide clouds, these are the clouds we see with our eyes on Jupiter. So clouds make things very complicated. They not only impact the chemistry of the atmosphere, but they can provide their own opacity. And so they can actually change the temperature pressure profile of an atmosphere. They can change what the emergent spectrum looks like dramatically. As a result of all of these molecules and condensates, the spectra, the emergent spectra of these objects are distinctly not Planckian. We like to tell our students a lot of times, oh, stars are Planck functions in zeroth order. You know, that's mostly correct. That is most definitely not true when it comes to these types of objects. So these are model spectra covering a range of temperatures from 3,500 down to 400, going from sort of red optical at 0.7. We see just shortward of this out to about 15 microns. The models are in black, and the corresponding blackbody curve for that effective temperature is shown as the sort of colored lines. And you can see, you know, maybe in the hottest object, it's looking Plancky, right, with a little bit of absorption due to water. But once you get down into these colder objects, it just looks nothing like a Planck function. There is no continuum like you normally see in a star. I'm going to go over here because I feel like and so, you know, for this object, you can be you can be super Planckian here, and you can be very much sub-Planckian here or here, right? And so you sort of go in and out. So when you think of an effective temperature, you sort of lose what that really means. It's not like it's a spot where it's just that temperature and all the light's coming from there. Another important property is that brown dwarfs have sizes which are effectively that of Jupiter. This is a mass radius plot. It's a bit old now, but I went to the website, he hasn't updated it, so I'm sort of stuck with it. If you're an Earth person, you can look at the bottom and the left axis. I'm not an Earth person, so those numbers don't mean anything to me. If you're a sun to star person, radii and solar radii over on the right, and mass is up at the top. And it shows the sort of mass radius relation for various things in the universe. So on the right, you have stars. Mass goes as sort of like radius, roughly speaking. In the lower left, you have planets like the solar system planets, right? Earth and Venus and Jupiter, Uranus and Neptune are in blue. And then you have lots of exoplanets in there. And then there's some brown dwarfs here in red. And what you can see is over this sort of mass range of, you know, a tenth of the solar mass down to Jupiter-ish, the radii are effectively constant, right? They're the size of Jupiter. Why is that? It's the competition between two equations of state. So if we ignore hydrogen burning stars for the moment, because that's different physics, when you're down here in the sort of rocky regime, you're building planets. If you add a rock to a rock pile, it gets bigger because the density remains constant, and so radius goes as mass to the 1/3 power. If you go to the other side where you have a lot of mass, say like a white dwarf, if you add mass to a white dwarf, it gets smaller due to its equation of state, and so the radius goes as mass to the -1/3 power. Because it's electron degenerate. And so these two sort of, you know, mass radius relations or equations of state have to meet somewhere, and they meet in the middle where the brown dwarfs are, and so you end up with a constant radius. And this makes studying brown dwarfs much easier because we know the radius. We don't, but we can at least assume it to a reasonable extent. So brown dwarfs are similar in size to Jupiter. They have molecular-rich atmospheres that evolve as they cool off. This is a plot showing sort of all the data, not all the data, but a representation of the sort of data that we have for all of the different types of brown dwarfs. So it goes from the red optical out to 15 microns. It's in sort of weird units of logarithmic f-nu. And at the top, you sort of have stars. Then you come down and you get into the brown dwarfs. You know, it looks nice, but this has been hard fought over 20 years. So there's Spitzer data that we're taking, where Spitzer is not being used anymore. There's a lot of IRTF data. There's PET data. There's Akari data. This was a Japanese satellite that sort of gets us in the mid-infrared here for the top three. So there's a lot of observations over 20 years. And we cover basically from red optical out to 15 microns. And so much of what we've learned about the hotter brown dwarfs come from that data. However, for the cooler brown dwarfs, the sort of wise dwarfs, this is what we have. It's really not impressive, right? We have sort of tens of spectra from HST in the near infrared, but it's very spotty. And then we have some photometric points from Spitzer and WISE. These are two space telescopes. And then there was some real heroic observations done by Brittany Miles and Andy Schemer on Gemini, where they were able to get some M-band spectra from the ground of, you know, 10 or so of these objects. But that's it. And so our understanding of these very cold brown dwarfs is really limited because that's all we have to play with right now. Enter Webb. Webb covers all of these wavelengths that we need, right? When cycle, well, now it would be like -3, but when the first cycle call came out back in 2017, I couldn't keep all the modes straight. And so I decided to make a figure for myself that had every possible mode of James Webb on there. So the top panel shows you a model of a brown dwarf, which is the thing I'm interested in, and then all the different spectroscopic modes, and then all the different photometric modes are down below that. And so this covers every wavelength you could possibly want for these cold objects. So Webb is the ideal facility for us to study these objects. So now I just want to briefly go into the Cycle 1 program and the basics of it before I show you some of the results we have. So the program goals are to obtain broad wavelength spectral energy distributions, cover as much wavelength as we can, to determine the bolometric flux, all right, that's the amount of energy that the object is emitting, and then because we know the distance to them, we can get the bolometric luminosity, one of the fundamental parameters of a star or brown dwarf. We can exploit the fact that the radii are effectively Jupiter to combine yourself to take the luminosity, use Stefan Boltzmann's law, and get a very precise effective temperature. That's a really useful thing. It turns out that once we do these observations, we can then compute the luminosity function of the entire 20 parsec sample, and then compare that to models trying to infer the underlying mass distribution. What is the mass function of these objects? It turns out that the underlying mass function is very sensitive to the number of cold objects. And so the Y dwarfs are a great place to do that. And then while not technically a part of the original program, because I ran out of space, and I didn't want them to think I was throwing the kitchen sink at them and everything I could do, even though the answer was that we could. We really wanted to also understand the atmospheric properties using both forward models and retrievals. And so today, I'm going to focus on 3 of these. The broad wavelength coverage, the determination of effective temperature, and then talking about the atmospheric properties. The mass function is sort of the last thing we're going to do. It's the last paper. It requires all the other papers to be written first. And so I won't talk about that today. Okay, so the details of it, it was a medium proposal. We got 75 hours of time on Webb, which was, I was shocked when they let that through, but I wasn't going to complain. We observed 24 late T and Y dwarfs. The way we built the sample was we took the 20 parsec sample, we eliminated all binaries, anything that was an odd spectrum that didn't seem to look right, and then we looked for objects that had parallax precisions, fractional precisions of less than 5%. So the distance is well known. And then we bin them into various absolute magnitude bins. And then on the y-axis here, you see the color, right? So this is Spitzer, channel 1 minus channel 2, or 3.6 minus 4.5. And you can see that at a given absolute magnitude, there's a huge range in color. And so we decided to try to go, sort of down the middle and then to the extremes of each of the bins to cover the sort of entire phase space. And we did okay. You might ask, why not just do the top and the bottom and the middle? There's constraints in observing time and how bright something is. And so this is what we came up with, and it's okay. So there's our objects. And then the idea is we're going to build these spectral energy distributions using NIRSpec Prism and MIRI LRS plus the imager. And the way we do that is as follows. So this shows you a model of an atmosphere. It's a 400 Kelvin object going from 1 to 40 microns. That's shown in gray. It's a high resolution model. We have HST ground data or HST or ground-based data for them out here. So we had this covered. NIRSpec Prism gets us all of this wavelength out to about 5 microns. And then MIRI LRS gets us spectroscopically out to 12 microns. And then we added 3 photometric points at 15, 18, and 21 microns. So that gets us almost the entire spectral coverage. And then to flux calibrate the spectra to make sure that they're at the correct absolute level, we use published Spitzer 4.5, and we grabbed another photometric band, F1000W, and that way it allows us to flux calibrate the data to a few percent. In cycle 1, they couldn't tell us, because they hadn't flown yet, what the precision out of the box the spectra would be. And so the numbers they were giving us was like, it'll be good to 15%. They expected it to be much better. but it'll at least be good at 15%, and that wasn't enough for us. We needed a better precision on the absolute flux level. So those are the observations. Okay, so now I'm going to talk about this one particular object. WISE 0359 is a wide dwarf. I just want to, because I like looking between these two figures. This is the, I showed you the data where we had some spectrum, a few photometric points, and an M-band spectrum in that sequence. This is that again. So this is sort of what we had pre-James Webb when it came to wide dwarfs, and it's kind of ratty, right? A little bit of spectra, some humps here, a couple of photometric points, and then a ratty ground-based spectrum. This is now what we have with Webb. Just absolutely stunning, right? My graduate student, looks at this and thinks, oh, this is just what we do, right? Whereas all the old people, every time we show these, we just sit there with this dumb smile on our face. It's just, this is what we've been wanting to do for 20 years, right? So here's the spectrum, it goes from 1 to 22 microns. It exhibits all the important carbon, nitrogen, and oxygen-bearing molecules that you want to look at in the atmosphere of an object. You have methane, you have water, you have ammonia, you have carbon dioxide, and carbon monoxide, all in one spectrum. I want to zoom in on just a couple of regions here. So the first one is going to be down at about 3 microns. A student was poking around, and he noticed a little divot. And so this shows you the intensity on the y-axis, and then the spectrum is shown in black with one signal uncertainty centered around 3 microns. And you notice this little divot at 3 microns, and you might go, well, that's 2 pixels, it's not statistically significant, but we decided to dig a little bit. Also plotted are cross sections for 3 different molecules. So we've got water, methane, and ammonia. And it turns out that there's a bump right at the same wavelength as our bump in ammonia. So this is the Q branch of the new one fundamental band of ammonia, and this had never been seen before. And I think in the paper we said tentative because it is a little nugent, and you might think, okay, there's something wrong with the data. We see it in all the other spectra, but we couldn't say that in the paper, so we said tentative. But we believe it's right. So this is the first time the new one fundamental band of ammonia has been seen in the spectrum of a brown dwarf. Let's now go to the 5 micron peak. This is a really rich region of the spectrum, and it's where a lot of the action is that we've now discovered. So this goes from like 3.5 out to 5-ish microns. Again, data are in the black. We've got 4 molecules plotted: water, methane, CO, and CO2. You have this gorgeous fundamental band of CO here with the band gap perfectly at 4.7 whatever microns. We see CO2. This is the first time we've seen CO2 in a wide dwarf. It's been seen in the hotter objects, but this is the first time we've seen it in a wide dwarf. And then you've got water and methane giving you all these other little wiggles and bumps in the data. And then finally, we'll go over to the 10 micron region. This is a really clean region of the spectrum. It's basically just ammonia. So again, 8 to 12 microns or so. The cross section is up there in whatever, yellow or orange or something. You see the P, the Q, and the R branch of this molecule really clearly. The double Q branch there is actually a result of inversion doubling. So nitrogen has 3 hydrogens. Sorry, yeah, ammonia has 3 hydrogens in a triangle, and so the nitrogen can either be on top or the bottom, and that's what gives you the doubling. So you get 2 Q branches in this particular molecule. All right, so one of the big questions is, what is the effective temperature of this object? So what's the definition of effective temperature? It's effectively Stefan-Boltzmann, right? So it's the 4th root of the bolometric luminosity divided by r squared, and then of course the bolometric luminosity is the bolometric flux times d squared, the distance. So we need F-bol. We've got to work backwards. With our very broad wavelength coverage, we can integrate over the spectrum. So we integrate from 0 to 21 microns. And then we have to add a little bit of a fudge factor for what's beyond 21 microns. We effectively drop a Rayleigh Jeans tail from 21 microns out to infinity to cover the rest of the wavelength coverage. And it's only like a 5% correction, which is tiny. Whereas previously, if you had to make up the difference, it was like 60% or something, right, from the other data. So this is wonderful. So there's our value for F bowl. Dave Kirkpatrick has done a lot of parallax work with Spitzer, so we know its distance is about 14 parsecs, which gives us the log of the bolometric luminosity relative to the sun of about minus 0.64. So it's 1,000,000 times fainter than the sun. I have a colleague who studies Wolf-Rayet stars, and he likes to mock me and say that you need 1 billion of your objects to be as bright as one of my objects, which is technically true, but there's more of mine than his. So, okay, so we've got the bolometric luminosity. What about the radius? We need the radius. So the first thing we do is just assume a default value, 1 Jupiter radii. It's the thing all around where people think of. So if you assume 1 Jupiter radius, you get a temperature of 450 Kelvin. That's pretty cold. But we can do slightly better than that. We can use models to try to infer what the radius would be. And the way we typically do this is we assume an age range of something like 1 to 10 gigayears. It sort of covers the age of the galactic disk. Yes, it could be younger, but we'll usually just say 1 to 10 gigayears. So what we do is we take the luminosity, which we have a value for, we have this age range, and we do a Monte Carlo simulation. So we assume the luminosity is drawn from a Gaussian with its mean and uncertainty, and then we assume the age is drawn from a uniform distribution between 1 and 10 gigayears. We go into an evolutionary model with those two values, we pull out the radius, and we do that 1,000,000 times. And the distribution of radii is what you see here on the left. Right. So here's 1 radius, and so 1 Jupiter radius. As you see, it's not 1 Jupiter radius, right? It does have a range around it. You might wonder what this thing is. I had to ask my students. I knew someone was going to ask me. It's deuterium burning. So when it burns deuterium for just a little bit, it slows the evolution down, and it sort of stays at a particular radius. You get a bunch of it. So here's the range of radii. And so now we have a luminosity distribution, and we have a radius distribution. We can make an effective temperature distribution. And so that's what this is. Here's the nominal 1 Jupiter radius temperature that I showed you, 452. And you can see that it's not a symmetric distribution. There's a box and whisker plot up at the top there. I think orange is the median. And, no, orange must be the mean, and the triangle is the median, and you've got the interquartile range in the box there. And so if you ask yourself, how do you summarize this distribution? If you just take the mean and you encompass 1 standard deviation of probability, you end up with a temperature of about 470 plus or minus 20 Kelvin. And if you're a median person, it's about 469, and then there's the interquartile range. And so this is a really precise effective temperature range, right? Taking into account the fact that we don't really know what the age is. The previous, uncertainties on the temperatures of these things were conservatively 100 Kelvin at like best, and you could argue 200 Kelvin. Right, 200 Kelvin at 400 Kelvin, that's not an impressive fractional uncertainty. And now we're down to 20 Kelvin. Okay, I now want to talk about fitting some models to this spectrum. We used a custom suite of models generated by Sagnet, and this is based on the Sonora grid from Mark Marley's group. I've never found a way to give the parameter ranges that just don't look like a box of text. I like doing things graphically, but I don't know what to do. So range of temperatures, 300 to 600 Kelvin. In steps of 25 Kelvin, we have a bunch of various surface gravities from 3 to 5.5. We have 3 different metallicities from subsolar up to solar at 0. And then there's this additional parameter, which I won't get into in this talk. Has to do with mixing in the atmosphere, which I will talk about in a little bit, but it's just another free parameter in the model. This is how it fits. Has a temperature of about, the best fitting model is a temperature of about 450 Kelvin and a surface gravity of about 3.25. Overall, it does a reasonably good job, right? I mean, it has bumps here, and then it gets the big bump, and then it sort of gets the 10 micron peak. And so if you're a theorist who works on this, you're very proud of this, because this is, this is 20 or 30 years of work by these theorists to build these models properly. However, as an observer, I'll be nitpicky and pick out little things that are wrong to bother them and help them improve things. So there's a couple of things here that aren't good. The near infrared does not fit very well. Turns out it's too hot, right? So the model is giving you too much light What that means is either we're seeing too deep into the atmosphere where it's very hot, or we're seeing to the right level, but it's too hot there. So something's wrong with the model in the near infrared. I should also point out that, oddly enough, I spent all of my life sort of in the near infrared doing things. And now I literally just ignore that wavelength range. I'm just like, oh, whatever, it doesn't matter, right? I spent the last 10 years working on this with WISE and getting HST spectra and trying to tease out all these little things. And now I'm just like, oh, that's just the tail, who cares, right? But it is important that we need to, get that right. You'll notice here at about 4.2 microns, there's this whopping absorption feature, right? There's this deep thing, that's a Q branch of the molecule, and then there's some absorption on the blue wing there of that 5 micron peak. That's phosphine. So there's way too much phosphine in this model. We don't see any phosphine in our spectra. If people are following brown dwarfs, you might have seen a paper by Adam Burgasser who claimed the discovery of phosphine. If you want to talk about that later, we can. I don't buy it. And we have a paper working on this now. But at least in this case, we don't see phosphine in the model. That's too much. And then out here at wavelengths which we've never probed before, but we have no data at these wavelengths for cold things. The photometry is just below the models, or I should say the models is above the photometry. And it looks very sort of scale factory, right? Like if I just multiply all of them by the same scale factor, they would fit. So I was really nervous that we screwed up some conversion, Jansky's to whatever, to this, to that, or the 0 point was wrong. And we looked through all of that and we couldn't find anything. So it looks like whatever's happening, the models just aren't fitting out of those wavelengths. And so it's something that we're gonna have to work on eventually. What mass and age do these effective temperature and surface gravity values imply? You can use evolutionary models to answer this question. So this shows you evolutionary models in the surface gravity temperature plane. So you have cold down at the left, something like 200 Kelvin up to 600 Kelvin, and you have surface gravity high at the top at 5 and low at the bottom at 3.25. The solid horizontal lines are the evolutionary path for objects of different masses. So the second one down, that's the path a 21 Jupiter mass object takes as it evolves over time. It's effectively flat because the radius is constant, right? And so since G is m on r squared, if r is constant and the mass isn't changing, the gravity shouldn't change. It's tilted a little bit because it does shrink slightly, right? It's not a fixed radius completely. So that's why it's tilted slightly. And then the dashed lines are the isochrones. And so, here's 20 million years, and up at the top is 10 billion years. If you put our object on there, the best fit goes way down at the bottom. That implies that it has an age of 20 million years and is a 1 Jupiter mass object. We don't believe that. That doesn't really make sense to us. That's a really low surface gravity. 20 million years, there's lots of things in the solar neighborhood and various moving groups and things that are 20 million years, and it doesn't seem like it's a part of one of those things. And surface gravity has always been a notoriously difficult thing to sort of get right when you're just doing these forward model fits. So we don't really believe that this is correct. In addition, it is inconsistent with the known luminosity of the object. So if you ask where in this Teff effective temperature gravity space an object with our luminosity would lie, it's in this band right here. And so it is nowhere close to that. So that's another thing that's telling you this is inconsistent. The solid line, the bolded line up at the top, is between 1 and 10 gigayears. So that's sort of standard age range that brown dwarf people use. And so if you just move that up, you say, okay, well, the temperature's right, but the gravity is wrong for some reason, it will plop right into that dark region. And if you do that, it becomes an object which is a few billion years old with, a mass of 10 to 30 Jupiter masses, which feels, a little bit better, at least. So this suggests that there really is something wrong with the inferred surface gravities of these objects using these models. Okay, let's talk about atmospheric retrievals of this object. So there are two complementary methods by which you can infer the properties of these objects. There's something called forward models, and just to make a connection, everything I talked about previously is a forward model. And so I'm just going to summarize how those are made. You start out with a set of small number of parameters, like say effective temperature, which sets the amount of energy passing through the atmosphere, surface gravity, which sets the pressure scale of the atmosphere, the composition of the atmosphere. And then if you're a brown dwarf person, you might add in some other things like clouds and mixing and that sort of stuff. So a small number of parameters. You assume as much physics as you can, things that you think you know, like the atmosphere has to be in radiative convective equilibrium. You will assume how the chemistry of the atmosphere changes as a function of temperature and pressure. You'll assume the abundances of the various species, or maybe the abundance ratios. You might change the C to O ratio or the luminosity, but all the ratios are fixed. And then anything else you can throw at it. You put that into a giant radiative transfer solver, and out of that comes the run of temperature and pressure in the atmosphere and the emergent spectrum at the top of the atmosphere. And that's the thing that you compare to observations. That's the red thing that I plotted on the data. There is an alternative method called atmospheric retrieval. This has its roots in planetary science in our solar system. So it goes back into the 60s and 70s. Mike Line, who's at the Arizona State University, brought this back into the brown dwarf community in about 2015. We started using this technique to study brown dwarfs. The idea here is you have lots of free parameters, like 20 of them. Each species of a molecule, say methane or water, has its own free parameter. It's the abundance of that particular species. And in this case, F stands for the volume mixing ratio, which is the number density of that thing divided by the number density of the entire ball of gas that you're looking at. So you've got like 10 there. You've got mass, you've got radius, that gets you surface gravity, which sets the pressure. And then you have to model, parameterize the temperature pressure profile. So there's a bunch of parameters that go into how the temperature and pressure change in the atmosphere. You make no assumptions about radiative convective equilibrium. You make no assumptions about abundances because they're all free parameters in this model. And then the idea is you optimize these parameters given the data. And when I first started reading these papers, it seemed like just black magic, right? And it was this panacea of all of our problems. And I never really understood it, but it's the simplest thing. It's fitting data to a line, right? So you've all probably seen linear data, and then you're like, I want to fit a line to that. So there's two parameters, right? There's the slope and the intercept. And you optimize those to sort of minimize least squares or maximize probability or something, right? And in that case, you can write down an analytical solution. In this case, we're doing the same thing, except the data is a spectrum, and the model is this 19-parameter atmospheric model for which you cannot write an answer down. But the concept of trying to optimize those parameters to fit the data is exactly the same. One of the things that I don't think we do enough is we actually write down our generative model. We have to assume that our data is being generated by some model. And so I know this is sort of getting nitpicky, but it's one of my bugbears. So this is the generative model we're assuming. So we're assuming our data is a random variable at some wavelength. It comes from the model spectrum, F nu, and it has a set of atmospheric parameters, those mixing ratios for each molecule, and then the temperature pressure profile and the mass and radius. We then convolve that with a known instrument profile to smooth the data to the resolving power of Webb. We then have to scale that by r squared over d squared because this model gives you the emergent flux at the top of an infinite atmosphere. So you have to deal with the fact that it's a sphere, and you have to deal with the fact that you're not on top of it, you're at some distance. And then, of course, we have to add noise. We have, it's a random variable, so we need another random variable. We assume that this extra term is drawn from a Gaussian with a mean of 0 and an uncertainty or a variance given by our observed uncertainties, plus this thing called a nuisance parameter, which allows us to sort of inflate the uncertainties. We assume the relative values are correct, but the up and down could be wrong, and it allows us to adjust to improve fits. So how do we get the parameters? Well, we use Bayes' theorem, which is given up there. So what that says is it's the probability density of those 19 parameters given the data is equal to your prior probability, which is P of theta, times the likelihood of the data given the model, which is the Gaussian part. And then you divide that by some normalization factor that in this case doesn't matter. This is not analytical. You can't write an answer down for this. Sometimes when you learn Bayesian stats, you can do all sorts of cool things and actually write down the posterior. You can't do that here. So we explore this 19-dimensional probability distribution using nested sampling at the Ohio supercomputer. And don't ask me what nested sampling really is, because I don't actually know. I mean, I know, but I don't really know. So it's a technique that allows you to explore, but I'm just saying words that don't mean it. This entire process, I don't want to imply that somehow we invented this whole thing. This is run in the Brewster retrieval framework, which was written by Ben Birmingham at the University of Hertfordshire in the UK. And so we've been working with him on this. So what do you get? You get this 19 parameter probability distribution. How do you display that in some useful way? I don't know what 19 dimensional thing looks like. You use marginalization. So this is the famous corner plot that you see in astronomy all the time. Basically, you integrate over all of the parameters you don't care about until you get the ones you do. So for example, on the upper left-hand corner, you see a little diagonal blue thing. That's what you're seeing there is the joint probability distribution for the abundance of methane and water, because that's down here. So what I've done is I've marginalized, I've integrated over every other parameter until you see that two-dimensional distribution. And then you can do it again, and you can just get the one-dimensional distribution, which is the Gaussian-looking things along the diagonal. Let's focus on the temperature-pressure profile to begin with. So previous work had very large credible intervals. These are effectively the uncertainties on the Bayesian parameters. So the only previous work that was done on Y dwarfs was by Zaleski in 2019. This was with Mike Line at Arizona State. They used our HST data from 1 to 1.6 microns to do retrievals on these atmospheres. They used a different retrieval code, but they're basically the same thing. And this is the results they got. So what this shows you is the run of temperature and pressure in the atmosphere. There's 0 degrees here, here's 1800 Kelvin here, and then pressure is inverted, it's logarithmic. So here's 100 bars, 0 is 1 bar, that's the pressure you're feeling on the top of your head right now, and then you go all the way up to 10 to the minus 3 or 1,000th of a bar. And so as you go into an atmosphere, as you fall into a brown dwarf, you get hotter and higher pressure, so you go down and to the left. So this is the inside of the brown dwarf, that's up at the top of the atmosphere. The black is the sort of median profile. It's the profile that you get if you assume the median values of all those posterior distributions. And then the red and the pink are the 1 and 2 sigma uncertainty buttons. And the median width of that is something like 200 degrees, right? And this is wonderful work that they did. Here's what we get with, shoot, one more thing, right. The other problem with this work is that it probes a very limited pressure range in the atmosphere. So what I'm showing here are contribution functions. So these are these sort of sideways Gaussian looking things. Each one of them is associated with a particular wavelength of the spectrum, and it tells you where in the atmosphere the light that you see at that wavelength is coming from. And so the idea here is if you integrate over this Gaussian in pressure, you will get the emergent flux at the top of the atmosphere. And so what this says is that the HST data probes these sort of regions of the atmosphere. And that's why the error bars get so big as you go up, because the data isn't actually constraining much up there. There isn't enough to really constrain the models, and so the uncertainties blow up. Here's what we get with Webb. We did the same thing. So we showed this at OWL, which is Jonathan Fortney's summer program, and it made him giggle. So you're sitting in the front, so I call this the Fortney giggle plot. So here is the temperature pressure profile we get from 0359. The median 1 sigma interval is 20 Kelvin. It's gone down by an order of magnitude. Right? It's just stunning. Absolutely stunning. I should have switched. This is now Partial's work. The previous stuff was all Sam's work. This is now Partial's work. Here's the contribution functions for Webb. Right? Or I should say, it's all the contribution functions for Webb, but the blue is the sort of longward of K-band, or longward 2 microns. And you can see how important the mid-infrared data is to constraining the upper layers of the atmosphere, right? We get all the way up to 1/10 and maybe up to 100th of a bar with the Webb data. So that broad wavelength coverage really helps you probe the entire important regions of the atmosphere. Let's look at the upper corner of the giant posterior distributions. The mass that comes out is about 14 Jupiter masses. The radius is about 0.9. It's close to 1, right? From mass and radius, you get surface gravity. So it's about 4.5. And then from radius and integrating over the model spectrum, you can get effective temperature, right? You get a luminosity out of it. And it's about 460 Kelvin plus or minus 20, which is feeling very similar to what we got previously. if we take those log G and effective temperature values and we plop it back on this diagram, things are looking much more reasonable, right? It's up in a region which is, you know, sort of where we think it's going to be. It's consistent with the luminosity of the object. And so, you know, with the retrieval, that's really telling us that there really is something wrong with inferring surface gravity using forward models for these things, right? I mean, it's just, I don't know, order of magnitude off in surface gravity. So something's really going on with these forward models that we don't understand still. One of the things we're really interested in, you know, I said these are complementary approaches. How does our retrieved temperature pressure profile match that of a forward model temperature pressure profile, the one where you generate the profile with all the physics you think you know? So these are two profiles. Ours is shown in the dark blue, and then the one that's to the lower left, the cyan-ish color, is an elf owl. This is another Marley version. They're naming all their things on Sonoran Desert things. So it's Sonora, and the elf owl, and I forget what the next one is, some other bird. And so that's we just pulled it from their grid. It's not exactly our temperature and gravity, so we've got to adjust that. But you can see that it doesn't match perfectly. And there's a weird kink at about zero, you know, log zero pressure. So about a bar in the atmosphere, ours is hotter by something like 200 Kelvin, which is interesting. And we don't know what that means yet, right? This is the first time we've done this, so we're still poking at this. But there is a difference. Let's talk about the abundances now of the species. So we did water, methane, CO2, ammonia. We also added hydrogen sulfide, potassium, sodium. These things are important because they impact the 1 micron region. That region I don't care about anymore, but it's important capacity sources. So they're there. And then we also added phosphine. And you'll notice that the phosphine abundance is 10 to the minus, you know, the mixing ratio 10 to the minus 10. There's no phosphine in this thing, right, according to the data. So let's look at the 1, 2, 3, 4, the top 5 there, the major carbon and oxygen variants and nitrogen variant species. The mixing ratios are about 3 to 5 times more precise than the Zaleski et al. Results. So the gray bar, the gray distributions are for an object very similar to ours that Zaleski studied, and then ours is in the red. And so we see that the precisions are much better. Even, you know, with methane, it's so precise that now we're seeing a difference with what they got. We would argue that the methane is lower than what they said. Water seems okay. There's no gray in CO and CO2 because they were unable to constrain those molecules because they don't exhibit any spectral features in the HST wavelength range. So they just set upper limits, but now we can actually measure. How well do these match the predictions of thermochemical models? And so what I'm going to show you are those predictions, and then I'll lay the data on top of it. So the idea here is that you want to come up with some chemistry scheme. This is all by Fisher et al. Several papers. I didn't want to put the years there. And the idea is you take your temperature pressure profile and you say, what are the mixing ratios of the various species along that temperature pressure profile, given this is how I think chemistry works for these molecules. And that's what's plotted here. So you've got the log of the volume mixing ratio. So high mixing ratio over here, it's 1,000, all the way down to 10 to the minus 10. And then log of the pressure inverted again, such that this is deep in the atmosphere, and at the top of the plot, you're at the top of the atmosphere. Water, so you've got water, methane, CO, CO2, NH3. And there's some, wait, do I talk about the windows? Yes, with decreasing pressure, so we're going to start at the bottom and work our way up. What do we see? We see that ammonia, which is in the orange here, as you go up, seems to increase its mixing ratio, goes to the right and goes up. So as you go up into the atmosphere, you get more ammonia. That's because as you go up into the atmosphere, it gets colder, and the nitrogen chemistry shifts from being dominated by diatomic nitrogen into ammonia. So that's why ammonia goes up into the right. CO and CO2 decrease dramatically, right? They go from here and they just shoot over to basically 0, right? At the bottom of the atmosphere. In fact, here it was methane. Methane is green, so it's this one here. You can see there's just a little kink this way, and that's because they are trying to meet down here where they would switch, where it got hotter, but we don't probe that layer of the atmosphere. So CO, CO2, the prediction would be you wouldn't see any of these things in the atmosphere. And then finally, you'll notice the giant kinks at the top of the atmosphere. What's going on there? So that's when ammonia and water eventually condense out of the atmosphere. So it gets cold enough that you literally just condense it out and it forms a condensate. The reason why ammonia comes back is because our temperature pressure profile at the top has a tiny little temperature inversion. So it gets just a little bit warmer, which then undoes the condensation. But we're not too worried about what's going on all the way up there because we don't really probe 10 to the minus 4 anyway. Here's where the data lie. Our abundances are uniform with altitude, right? It's just one number. We can't figure out what the abundance is at every layer of the atmosphere because the parameter space would explode to 1,000 parameters. And we simply can't do a retrieval with 1,000 parameters. So these are uniform with altitude, okay? So methane and water, they do a pretty good job actually. They're relatively close to what you would predict for thermochemical equilibrium. CO and CO2, however, are not, right? Here's CO, here's CO2. They're saying we should have almost nothing, and yet we've got quite a lot of CO and CO2 in the atmosphere, according to our retrieval. And then ammonia seems to be lower than it should. And you might think, wow, the chemistry is horrible. They really don't know what they're doing. But that's not actually what's going on. And so let's talk about what's actually going on here. It turns out that mixing within an atmosphere can impact the abundances of important absorbers. So here's a cartoon, still with some DDA from like 20 years ago. He gave a talk, and I thought it was just a great way to explain this. So all credit goes to DDA Simone. So we have in the bottom of the plot, we have a very deep, hot interior, and then at the top, you're shallow and very cool. When you're deep and hot, the carbon chemistry is primarily in CO. That's the dominant carbon-bearing species, so CO is more abundant than methane in equilibrium. The top of the atmosphere, it's the opposite. It's cold, the methane gets going, and you have more methane than CO. Okay, and that's what you would predict in equilibrium. And to zero order, that is what we see. However, if you start mixing the gas around, right? So you might bring CO-rich gas into the upper atmosphere, and you might pull methane-rich gas down out of the upper atmosphere. And this happens at some characteristic time scale, the mixing time scale it's called. So we have that process. And then you have to talk about how the species are converted into each other. So it turns out that it takes a long time to convert CO into methane. And so this time scale, it can range, it's like 10 orders of magnitude. So, when you're very cold and low pressure, it's like 1 billion years or something. It's the time scale. It's ridiculous how dramatic this time scale changes. So the problem is that you are mixing gas and you're struggling to get it into equilibrium. And so if the conversion time scale is much, much larger than the mixing time scale, then you end up with excess CO in the upper atmosphere. Methane still dominates, but you've got all this CO up in the upper atmosphere that's being mixed up, and there's just not enough time for it to get converted into methane to come into equilibrium. And so it just sits up there, and you can see it spectroscopically. And so that's why we get to see these molecules in the atmosphere. So it happens for CO, it happens for CO2, same exact process, and it also happens for ammonia, the nitrogen chemistry. In this case, what's in excess is diatomic nitrogen in the upper atmosphere. Diatomic nitrogen is a homonuclear molecule, so it doesn't radiate in a dipole approximation, and so it's not spectroscopically active. But what that means is you have a deficit of ammonia because you have an excess of N2. You're bringing the ammonia down very quickly. So in the nitrogen chemistry, the thing that you can see, which is ammonia, you should have less of than you would predict in equilibrium. And that's exactly what we see here. So we see CO and CO2 at much higher values than you would necessarily predict from just thermochemical equilibrium, and we see ammonia with a smaller value than you would predict for thermochemical equilibrium. I didn't add this into this, and if you're interested, we can talk about it later and at the end of a few slides. You can actually use these abundances to measure the vigor of mixing in an atmosphere. And we're starting to find some interesting things on that, but I don't have time to go into that. Here's the model spectrum that comes out of the retrieval. So 1 to 12 microns. The bottom is the residual, mostly random residuals. I mean, there's some weird things going on. There's an issue down here at 1 micron. You can see that there's a 25% decrement. That's those potassium and sodium. I said it impacts around 1 micron. These are doublets, they're resonant doublets that sit down at about 6,000 or 7,000 angstroms. And their wings are so broad due to pressure broadening that they extend all the way out to 1 micron. And that's a very hard thing to model quantum mechanically, so the opacities are not well known. So that's what's going on over here. But again, it's the near infrared and we don't care about that. So. One thing we were really interested to ask is how sensitive are the results to our assumed temperature pressure profile model. I haven't actually told you what that is yet. But the one I've been showing you is a 5-knot spline. So we have a spline point at the top of the atmosphere, the bottom of the atmosphere, the middle of the atmosphere, and then 2 intermediates. And then so the positions and temperature of those are model parameters, and then you fit a spline through those, and that's the temperature pressure profile that you run through the radio transfer solver. So there's 5 free parameters. So we're like, yeah, is that a problem, right? We have this broad pressure atmosphere. Maybe that's not what we wanted. Maybe you need to do 10. Turns out nested sampling, when you're doing 10 knots, takes infinity of time. So we couldn't do it with nested sampling. We really want to use nested sampling for various reasons. You can do it with Markov chain Monte Carlo, but we don't like that as much. So we decided to try something different, which was use a parameterized atmospheric model. So this is the Mann-Hoogsteden and Seeger model from back in, I didn't put the year, 20-something, I think. It breaks the atmosphere into 3 layers, and there's various parameters that control what happens to the atmosphere. And it turns out there are 5 additional free parameters here. So we just swapped one parameter, one model for the other, and then ran the retrieval. And this is the difference we get in the temperature pressure profile. Overall, not bad, right? It's not like it's dramatically different, so we're not wrong. But there's some interesting differences deep in the atmosphere. We're getting deltas of 100 Kelvin or so. Certainly these are broad, but still this looks real. So the assumed temperature pressure profile actually does matter, right? It's not just pick whatever you want. It matters. So we need to do a lot more investigating on this. How does it impact the abundance ratios, or the abundances? The red is the 5-knot, the green is the parameterized model. Overall, again, not horrible. There's some interesting differences, like in ammonia, hydrogen sulfide, very different. Don't know what that's about. The mass is odd. We really don't understand what's going on there. The parameterized one basically doesn't really constrain the mass at all, and so that's interesting, especially since it's just deep in the atmosphere. We're not sure what's going on there. These are all things that we're still working on, but it makes a difference. That's the point that I want to. So the future work in this retrieval analysis is to perform a systematic study of all 24 of these objects, or expect for 24 of these things. And so we really want to provide robust statistics on the abundances of the major gas species. This is one object. You could say it's up in an oddball. That's why this is that. So we want to do it for all of them to see what we get, and also look for trends with temperature, right? We do span several hundred degrees in temperature, and we see a trend in temperature. And then the other thing that we're really looking into is including clouds in the retrievals. There are several cloud species, potassium chloride, sodium sulfide, I think, and then in principle water that can form in these atmospheres. And the idea is, do they make a difference? There's conflicting discussions in the literature. Some people say the Y-J color of these things implies clouds are forming, but yet you don't really see any impact on spectra. There's disagreements about the cold brown dwarf, whether there's water clouds in that or not. Some people say yes, some people say no. So the hope is that we can do this with the retrieval. And the reason why we want to use nested sampling is because it gives you that normalization factor, right? Which I sort of just brushed off, because for parameter estimation, you don't care about a normalization parameter. You just want to know what the distribution looks like. But that thing is called the evidence, and it's a way of ranking models. So we'll compute with clouds, without clouds, and then if you assume equal prior probabilities of both being the same, the ratio of those values gives you effectively a probability. And so we'll look for things that are 3 or 4 sigma significant between cloud and cloudless. I do okay on time? Or am I over? Over. Okay, I'll just stop. Sorry, it's the first time I've done this full talk, so I don't have full time. So my apologies for going over. Webb is providing stunning spectra of brown dwarfs. There's a lot of work by Jackie Faraday, her group. I recommend going and seeing her work. We're able to measure effective temperatures to 20 Kelvin. 4 models do a reasonably good job. Retrievals are showing a lot of promise in understanding these. And then stay tuned for a lot more exciting results to come in the future. Thank you.